Hello there, my boosted brethren. Today we are going to shine some light on a sneaky villain that lurks in the shadows of our turbocharged engines, turbo compressor surge. So buckle up and prepare to dive into the nitty-gritty of this notorious nemesis. So picture this, your right foot is planted, the wind's flowing through your mullet, your precious little turbocharger, that powerhouse of air compression is spinning at 100,000 RPM, working its magic, delivering that sweet, sweet boost. Everything in the world is well. But trouble is brewing. Lurking in the near future is something that threatens to derail your turbo-turning titillation. That's right, it's compressor surge, and it's here to tear the insides clean out of that turbocharger and spit parts all over your engine bay. All right, that's a little dramatic, but if you read some of the internet forums, that's the way it seems. So what exactly is compressor surge, and does it really destroy your turbo? All right, let's tackle the first question first. What is compressor surge? So if you were to read the engineering textbooks, you get an explanation something along the lines of compressor surge is violent airflow oscillating in the axial direction of the compressor. Whoa, but what does that mean? Well, it means that normally air flows this way through the turbo, but sometimes it pushes back out the wrong direction this way. So how does that happen? Well, the easiest way to picture this is to imagine that we're cruising along, building boost, then suddenly, snap, the throttle goes closed. Now we've got all this built up pressure in the intercooler and intake piping, but because we've snapped the throttle closed, air is no longer flowing into the engine. That air is trapped in the intercooler piping and it has to find the path of least resistance, which is often out the way it came in, through the compressor housing of the turbo. This causes an audible chopping or fluttering noise as air escapes back out through the turbo's compressor wheel. Now, contrary to common belief, this does not spin the turbo back in the wrong direction. In fact, the turbo tends to maintain a fairly constant RPM during compressor surge, which makes sense because the turbine wheel is still being turned by those exhaust gases. Now, many of you would be familiar with these turbo compressor maps. On the x-axis we have compressor flow, and on the y-axis we have pressure ratio. And then there's all these efficiency lines, and most importantly for this conversation, there is the surge line. This surge line represents the point at which the turbo's compressor wheel can no longer maintain its grip, for lack of a better word, on the air going the normal direction into the intake piping of the engine. And as you can see from the compressor map, this is a function of both pressure ratio and flow rate. Now, flow rate is just the measurement of total airflow passing through the turbo's compressor, and pressure ratio is the ratio of pressure between the intake air pressure before the turbo and what's coming out of the turbo into the intercooler piping. What happens on the compressor map when the throttle is closed is the engine is no longer ingesting all of the air that the turbo is pushing out. So the flow through the compressor drops, sending us this way on the compressor map. The pressure in the intercooler piping, it hasn't dropped. If anything, it's rising because the turbo is still spinning, pushing more air into the pipework. So the pressure ratio is actually increasing, and eventually we cross the surge line. Now at that point, we get aerodynamic stall or flow separation at the compressor wheel. And that is just a fancy way of saying, yeah, I know what you're thinking. Why is it and not just? Well, there's actually a good engineering explanation for that too. When we get this flow separation, there's a local pressure drop at the compressor wheel as air flows axially back through the turbo, which pushes us back into the normal operating area of the turbo's efficiency map. The compressor wheel regains its grip on the incoming air, and we get normal airflow conditions again for a moment. This is short-lived because the throttle's still closed, meaning they're still in a low flow condition, and the cycle continues. Thus, the fluttering noise. So this is what causes the oscillating or the chopping noise. It's air flowing normally through the turbo one direction and then being stopped as the compressor wheel loses its grip on the normal flow of air, the pressure drops, compressor wheel regains grip on the air, and the cycle continues. On the compressor map, we're crossing back and forth across the surge line when this happens. So snapping the throttle closed is the most common cause of turbo compressor surge. But there are some rare circumstances where it's possible for the surge to occur when the throttle's open. So heading back to our compressor map, compressor surge can occur in some circumstances where there's low RPM and therefore low total airflow through the engine, the turbo can sometimes produce enough boost to push into the surge area. Now this phenomenon is more prevalent on small capacity engines, which makes sense because a small engine has lower total airflow at any RPM. In this situation, the only option outside of a complete redesign of the turbo is to reduce your target boost in the low RPM area of the boost control map so that you're never crossing the surge line. Alright, so now you're all compressor surge experts. The big question is, should I expect my turbo to spontaneously disintegrate into a million pieces at the first sign of compressor surge? Well, not really. I mean, it's not great either. The way I like to think about it is compressor surge is to a turbo what knock or detonation is to an engine. It's an uncontrolled action where pressure is released outside of the normal operating conditions of a component. In a turbo, when the regular airflow out of the turbo into the intake piping is disrupted with oscillating airflow in the axial direction of the compressor, the direction of loading on the bearings of the turbo shifts. And that's where the real damage comes from with compressor surge. It's the loading and unloading of the bearing surface that causes the damage. Not the first time it happens, not the second, but as time goes on, wear increases. Similarly, the more boost the turbo is making at the time of surge, the greater the impact on the bearing surface. Alright, so what do we do about all of this? Do we just drive around being very gentle on the throttle and never close it fast enough to induce surge? I don't know, maybe the opposite. Maybe we just never lift. Now while that might sound nice, it's not really realistic. No, you probably already know where I'm going with this. We install one of these guys, a blow-off valve. When the throttle closes, this clever little device opens up, allowing that built-up pressure in the intake piping to escape, preventing compressor surge and saving our turbos from the recycling bin. So nothing is more synonymous for the turbocharged engine than the sweet, sweet whooshing noise of a blow-off valve. Well, let's be real here. We all work with that one guy who walks past your workstation every day making blow-off valve noises. You know the guy. Go ahead and tag him now in this video. So let's pull apart one of these blow-off valves and we'll look at how they work. So inside the valve, we have a spring-loaded piston that is normally closed. At the top, we have a vacuum reference that goes to the intake manifold after the throttle body. What happens is, when the throttle snaps closed, we get vacuum at the top of the valve, which effectively pulls on the top of the piston. We also have positive pressure in the intake piping that's pushing the bottom of the piston up. This push and pull on the piston overcomes the spring pressure and opens the valve. Once the blow-off valve is open, two things occur. One, there is a pressure drop in the intake piping, and two, there's an increase in flow through the compressor. The outcome is our turbo no longer ends up in the surge area of the compressor map. Now, contrary to common belief, selecting a blow-off valve is not just all versus but rather, selecting a blow-off valve should be all about speed and flow. Can the valve open fast enough and flow enough air to prevent the turbo from going into surge? And for this reason, there really is no one-size-fits-all blow-off valve. If you're running a stonking big turbo at very high boost, you're going to need a blow-off valve that can bypass a whole lot of air when you back off the throttle. In this case, you're probably going to want to go with something like the power port blow-off valve. This guy here can flow over 600 cubic feet per minute worth of air, and it's got a nifty dual chamber design that allows it to be hung open during the staging and launch control sequence in a drag car. Now, if on the other hand you're running a smaller or an OEM turbo, perhaps you just want to keep a low profile on the street and not attract too much attention. In this case, you may want to go for something that recirculates the air back into the intake system. This recirculation of air is often called a plumb back blow-off valve. And rather than venting the excess pressure straight out into the atmosphere, creating that characteristic noise that a blow-off valve makes, a recirculating blow-off valve puts that air back into the air intake prior to the turbocharger. In this situation, you may want to consider even one of Turbosmart's direct OEM replacement blow-off valves in the compact range, or maybe the Sparkport range. Or maybe, like me, you just want to keep all of your options open and have silent operation when cruising around town, but let the world know that you mean business when you turn up the boost. And for this situation, there are these dual port blow-off valves that allow you to have sort of the best of both worlds. recirculate under light load, and then vent to atmosphere when the pedal hits the metal. So there really is no one blow-off valve that fits everybody, because everyone's requirements are just a little bit different. Selecting the correct valve for you is going to be a balance of flow requirements, fitment options, speed of operation, OEM integration requirements, and for some, most importantly, audible pleasure. So what have we learned here today? Firstly, compressor surge is not only an enemy of performance, but also a threat to the longevity of your turbocharger. Without a blow-off valve, the turbo experiences oscillating flow across the compressor wheel, causing unnecessary strain and wear on the turbo components, potentially leading to premature turbo failure. A correctly sized blow-off valve that opens quickly and allows enough air flow to prevent compressor surge can extend the life of your turbo, as well as sound like music to a turbo lover's ears. And most importantly, Turbosmart offers the world's largest range of blow-off valves and diverter valves. There's one to suit just about every application that you can think of. So why don't you head over to our product page on our website turbosmart.com to check out all the options and see which one might be right for you. Well, that's all we have time for on today's video drop. If you want to dive deeper into the world of turbocharged engines and stay up to date with all things Boost, be sure to hit the subscribe button, ring the bell, and join our turbo loving community. So until next time, keep the Boost alive.